if you reach into your pocket right now, you are holding a device that operates on just this fundamental scientific mismatch.
Oh, absolutely.
Like, it's a piece of technology built by engineers who know absolutely everything about how its signal passes through, say, the concrete wall of your apartment building.
Right.
But, and here's the terrifying blind spot, the biologists who are actually studying the health impacts of that exact same device. They've never actually tested what happens to a human being sitting behind that wall.
I mean, it is a massive institutional gap.
Yeah.
We have these two incredibly advanced scientific disciplines, right? And telecommunications engineering and bioelectromagnetics. And for decades, they have essentially been speaking completely different languages.
And today's deep dive is really about what happens when someone finally forces those two worlds to talk to each other.
Yeah, it's fascinating.
Because if you're listening to this, we're untangling two highly detailed internal research documents, both authored by Stephen Sears' work back in August of 2026. And on the surface, I mean, these documents look like they belong in completely different filing cabinets.
Oh, totally.
One is this granular, mathematically dense autopsy of the biological effects of cell phone radiation. And the other, well, the other is a futuristic design brief for a tactile sensory communication garment.
Like a suit.
Right. A suit that aims to literally make you feel human speech through your skin.
Yeah, and they read like a detective story.
They really do.
Because the clues to building this futuristic suit are actually hidden in the history of scientific failures, the electrical resistance of human sweat, and this decades-old misunderstanding about radio frequencies.
Wow.
The author basically realized that the profound mismatch between how our technology transmits information and how our physical bodies actually receive it, that's the key to solving both of these mysteries.
So we are going to unpack this, and we have to start with the first document, which is all about electromagnetic field.
Right, the bioeffect.
Yeah, and to my absolute surprise, this investigation into the digital devices we carry in our pockets every day starts with chicken embryos.
Yep. Chickens.
Specifically, exposing fertilized chicken eggs to magnetic fields. I just have to ask, why on earth are we starting in a poultry lab in 1994?
I know it sounds bizarre, but we start there because the author is tracking down the absolute origin of the public panic surrounding digital devices.
Okay.
To do that, he highlights a foundational study by Ubeda and colleagues from 1994.
Right.
What Ubeda did was take freshly fertilized chicken eggs, put them in an incubator, and basically surround them with magnetic coils.
Like just standard magnet.
Electromagnets, yeah. And for the first 48 hours of development, these embryos were just bathed in a pulsed magnetic field.
So just a magnetic field turning on and off?
Yes, but the parameters are what really matter here. The field pulsed 100 times a second with a peak amplitude of 1.0 microtesla.
Is that a lot?
Not at all. For context, the Earth's natural magnetic field is around like 50 microteslas. So this is a very, very weak field. But the critical variable Ubeda tested was the shape of the pulse, specifically what we call the rise and fall time.
Meaning how fast the magnetic field snaps to full strength and how fast it drops back to zero?
That is the core mechanism, yeah. They compared a slow rise time, which they called PMFA, that took about 85 microseconds to build up and fade away.
Okay.
And they tested that against a very fast rise time, PMFB, which snapped on and off in just 2.1 microseconds.
So PMFB is incredibly violent, relatively speaking. Like it's a sharp, aggressive spike.
Exactly. And that sharpness completely dictated the biological outcome.
Wait, really?
Yeah. After the 48-hour exposure, they let the eggs incubate normally in a field-free environment.
Right.
The fast rise time pulse, that sharp snap of PMFB, produced a staggering threefold increase in early embryonic death and developmental anomalies.
Threefold?
Yeah. Meanwhile, the slower wave, the 85 microsecond one, barely moved the needle. I mean, it didn't even reach statistical significance compared to the control group.
A threefold increase in death just from changing how fast the magnet turns on.
Yep.
How does a magnetic field even do that to a biological cell?
Well, we have to look at Faraday's law of induction.
Okay. Take me back to high school physics.
Right, so a changing magnetic field induces an electrical current in a nearby conductor.
And the conductor here is The egg.
Exactly, the conductive saline environment of the embryonic tissue itself.
Got it.
So the faster the magnetic field changes, which physicists denote as dB over dt, the stronger the electrical current induced in the tissue.
Oh, I see.
So the slow wave just didn't induce enough current to bother the cells. But the fast wave induced a current strong enough to disrupt cellular processes during this really critical window of development.
Wow. Okay, so that is terrifying.
It is.
But usually in science, one study is just a starting point. Like a single lab can have a weird batch of eggs or a calibrated machine that's just slightly off.
Which brings us directly to the second foundational paper the document analyzes.
Okay.
This is the Berman et al. Study from 1990, famously known in the bioelectromagnetics world as Operation Henhouse.
Operation Henhouse. You really have to appreciate scientists with a sense of humor.
It definitely sticks in the memory. But this was a massive, unprecedented replication effort.
Really? How big?
6 different laboratories across Canada, Spain, Sweden, and the U.S. agreed to run the exact same experiment.
Oh, wow.
They used identical equipment shipped from the same manufacturer, an identical protocol, identical unipolar pulsed fields, 100 pulses per second, 1 microtesla peak, and a fast 2 microsecond rise time.
So they were trying to lock everything down.
Exactly. This was the gold standard attempt to prove once and for all that these low-frequency magnetic pulses actually harm development.
Identical equipment, multiple countries. I mean, if the effect is real, it should show up everywhere, right? What happened?
Well, 5 of the 6 laboratories showed more anomalies in the exposed embryos compared to the controls.
Okay, so it is real. The fast magnetic pulse disrupts development.
We have to look closely at the statistics here, because this is where the mystery really deepens.
Oh.
Out of those 5 labs, only 2 reached statistical significance. Wait, really?
Yeah. When they pooled all the data together across all 6 sites, the overall difference was significant. It was about 25% abnormalities in the exposed group versus 19% in the control group.
Okay, so a bump, but not huge.
Right, but the glaring issue was this massive statistical interaction between the incidence of abnormalities and the laboratory site itself.
Wait, you mean the biological effect actually depended on which country or which specific room the eggs were in?
Yes. The interlaboratory variability was entirely unexplained.
That is wild.
It could have been the local geomagnetic field, the ambient temperature, maybe just subtle differences in handling something local was interacting with the experiment.
Oh, man.
And the author of our document notes that later attempts by other researchers to replicate these findings just outright failed.
Really?
Yeah, a team led by Maffeo failed twice in the 1980s. Another researcher named Martin found an effect at one frequency, but not another.
So we are dealing with a textbook replication crisis.
Yeah.
Like, the data is incredibly messy. As the document bluntly puts it, this is an effect that simply does not travel between laboratories.
Wow.
Ultimately, the International Commission on Non-Ionizing Radiation Protection, ICNIRP, reviewed all of this and concluded that these low-frequency fields are unlikely to have adverse embryonic effects simply because the data is just too inconsistent.
Okay, so we have this murky, controversial history of exposing chicken embryos to extremely low-frequency magnetic pulses.
Right.
But hold on, I need to push back here for a second.
Sure.
You beta-exposed eggs to magnets. Cell phones don't use magnets to connect your call. They use radio waves. Why is the author even looking at a magnetic field study to understand cell phone radiation?
You have just identified the great conflation.
The rate conflation,
Yes, this is the core misunderstanding in public discourse that the document completely dismantles.
Yeah.
The public hears cell phone radiation and immediately points to these chicken embryo studies as proof of harm. But they're conflating 2 totally different physical exposures.
Let me try an analogy here to see if I'm getting this.
You go for it.
Imagine I have a massive heavy-duty flashlight.
Okay.
Pointing to the chicken studies to prove cell phones are dangerous is like worrying about getting a heat burn from the light bulb, which represents the radio frequency connecting the call, when the biological effect the scientists actually tested in the lab was the magnetic pull of the heavy batteries powering the flashlight.
That is a phenomenal way to visualize it. Yes.
How sweet.
Because the physical distinction between the bulb and the battery changes absolutely everything.
Right.
U-beta's parameter, that fast-rising pulse that caused embryonic death, is a near-field, magnetically coupled, extremely low-frequency exposure. We can call that exposure A.
The battery pull.
Yes. Its entire mechanism relies on that rapid change in the magnetic field, inducing a current in the tissue.
Right.
But a Wi-Fi or cellular transmission from the antenna, The radio frequency connecting you to the tower is exposure B.
The light bulb.
Exactly. It is a sinusoidal radio frequency carrier operating at gigahertz frequencies. When human tissue interacts with an RF carrier, it is not experiencing a magnetic pulse that induces a current. It experiences dielectric heating.
Meaning the tissue absorbs the energy as heat, kind of like how a microwave oven works, but obviously at a much lower power.
Exactly that mechanism. It is dosed in watts per kilogram, which the industry calls the specific absorption rate, or SAR.
Right. I've seen SAR values listed in phone manuals.
Exactly. Now, if you look at an RF signal on a spectrum analyzer, it might look like a blocky square wave turning on and off, but that square wave is just the modulation envelope.
Okay.
The biological tissue itself does not experience that envelope as a magnetic pulse.
So the activists pointing to the henhouse studies and screaming about cell phone antennas are pointing to the wrong physical phenomenon entirely.
They're completely missing the physics.
Wow.
But here is where the document takes a massive, unexpected turn.
Oh.
The author points out that while the RF antenna doesn't cause these low-frequency magnetic pulses, the digital device itself actually does produce a real extremely low-frequency magnetic near field.
Wait, where is it coming from, if not the antenna?
From the hardware.
The hardware?
Yeah. It is an unavoidable byproduct of the device's internal circuitry. The battery current, the power management chips, the display drivers lighting up your screen.
Oh my God.
When your phone draws power in sudden bursts to process data or refresh the display, it creates incidental magnetic fields in the exact frequency range around 2 hertz to tens of kilohertz that Ubeta was testing.
So the low-frequency pulses are real, but they're a hardware side effect, not the intentional communication signal.
That is the staggering irony. The public was terrified of the antenna when the real physical overlap with the lab literature was actually coming from the battery in the screen.
I mean, that is wild.
And the document notes this stunning reality. This specific exposure, the incidental magnetic field from the device hardware, is physically analogous to Ubeta's experiment, but it has never actually been studied developmentally using actual device waveforms.
That is just crazy to me.
Right.
The scientists tested lab-generated pulses. The engineers built phones that accidentally generated similar pulses, and nobody ever put the actual phone in the incubator to see what would happen.
Exactly.
Let's dig into what the phone is actually emitting then, because the document goes deep into the weeds on something called the 217 hertz signature of GSM networks.
Oh, yeah.
And if you're listening and you're old enough to remember having a cell phone near a desktop computer speaker in the early 2000s, you'd hear that weird, rhythmic sound right before a call came in.
I remember that sound vividly.
Right.
That acoustic interference is the exact signature the document analyzes.
Okay.
And to understand where that rhythm comes from, we have to look at how GSM, which is the classic 2G cellular standard, how it manages traffic.
Okay, break that down for us.
It uses a system called time division multiple access, or TDMA.
How does time division work?
So imagine a continuous timeline divided into repeating frames. Each frame lasts exactly 4.615 milliseconds. Inside that tiny window of time, the frame is sliced into 8 individual time slots.
Right.
When your handset is in a voice call, it does not transmit a continuous radio wave. It only transmits during one of those 8 slots per frame.
So it takes turns sharing the frequency with up to 7 other phones.
Yes.
It talks, then stays silent while the others talk, then it's turn again.
Yes, it is rapidly time-sharing. So your phone fires a microsecond burst of radio frequency, goes quiet for 7 slots, then fires again.
Wow.
And if you do the math, 1 transmission burst every 4.615 milliseconds, you get a repetition rate of 216.7 hertz.
Okay.
That is the famous 217 hertz signature. It is literally just the rhythm of the transmission bursts.
Okay, a rhythm of 217 hertz. That sounds dangerously close to the 100 hertz pulse Ubeta used to kill the chicken embryos. I could definitely see why people panic.
It sounds identical on paper, but this is the crucial distinction that decides the entire safety argument.
All right, hit me.
We have to zoom in on what happens inside that tiny microsecond burst of transmission.
Okay.
At a 900 megahertz frequency, which is a standard GSM band, a single one of those transmission bursts contains nearly 500,000 individual carrier cycles.
500,000 distinct waves packed into a fraction of a millisecond.
Yes. Because there are so many cycles packed into that burst, the actual spectrum of the signal is extremely narrow.
Right.
The sidebands, which is the spread of frequencies bleeding out around the main 900 megahertz carrier, they only sit at roughly 1.8 kilohertz away.
Okay, so what does that mean practically?
It means the physical frequencies actually being broadcast by the antenna into the air are essentially 900.0018 megahertz.
I think I see the mechanical difference here.
There is zero, absolutely zero, 217 hertz field component in the radiated RF spectrum.
Because 217 hertz is just the rhythm of the envelope turning on and off.
Yes.
It's not the frequency of the physical wave itself.
You've got it. The 217 hertz only exists as an envelope shape. For human tissue to feel that 217 hertz rhythm as a biological signal, something in the tissue would have to act as a rectifier.
What does a rectifier do in this context?
Think of a biological demodulator.
Okay.
It would be a cellular structure capable of taking the gigahertz signal, stripping away the 500,000 high-frequency waves, and leaving behind only the low-frequency rhythm of the envelope.
And does that exist?
As the document explicitly states, no biological demodulator has ever been identified at gigahertz frequencies.
Wow.
And from a thermal perspective, the envelope is totally irrelevant anyway. Human tissue takes seconds to heat up or cool down, but these bursts happen in microseconds.
So the tissue just averages the heat out.
Exactly.
So the whole activist hypothesis that the modulation matters, that the 217 hertz rhythm of the RF signal is biologically active, is based on a physiological mechanism that simply doesn't exist to the human body.
That is the author's definitive conclusion.
Okay, but we circle back to the hardware.
Right.
If the antenna isn't emitting this low-frequency pulse, why did researchers historically measure huge low-frequency fields around cell phones?
It comes right back to the battery draw.
The flashlight battery.
Yes. The document cites historical measurements of actual devices. Older GSM handsets produced a 217 hertz magnetic component of around 1 microtesla, just 3 centimeters from the front of the phone.
Okay, 1 microtesla, that matches U-beta.
It does. But some surveys found maximums of 22.4 microteslas, or even up to 70.03 microteslas in the 5 to 200 hertz band.
Wait, 70 microteslas?
Yes.
U-beta only use 1 microtesla to cause the embryonic deaths in the lab.
That is the bombshell. The incidental magnetic fields produced by the circuitry of older phones far exceeded the levels used in the lab studies.
Oh my God.
The public was protesting cell towers, entirely missing that the real physical overlap with the developmental literature was sitting in their pocket, generated by the screen and the battery.
So if I have a modern smartphone in my pocket right now, should I be panicked about the battery pull?
Well, here is the unexpected good news.
Oh, thank goodness.
The generational trend of technology is actually pushing us away from this specific risk. The tech industry solved this biological problem completely by accident.
By accident. How did they manage that?
It comes down to how modern networks manage data and power.
Okay.
Older GSM networks use those sharp, discrete, time-divided bursts of transmission that cause sharp, discrete spikes in battery draw.
Right, snapping on and off.
The battery was violently waking up and going to sleep hundreds of times a second. That violent snap is what created the low-frequency magnetic pulses, the high dB over dt.
Okay, so what changed?
As we moved to 3G, or WCDMA, the transmission became continuous. The battery draw smoothed out.
So no more sharp snaps on and off.
Exactly. And let's look at LTE and 5G. The uplink in modern phones is scheduled and based on a technology called orthogonal frequency division multiplexing, or OFDM.
Okay, you're going to have to translate OFDM for me.
Imagine the older 2G GSM network as a single giant fire hose.
Okay.
The phone turns the fire hose on full blast, then snaps the valve shut violently. That jarring snap causes a huge physical shock to the plumbing, in this case, a massive power spike in the battery.
Got it.
OFDM is more like a carefully managed sprinkler system.
Okay.
Instead of one violent fire hose, the phone shoots dozens of tiny, continuous, highly managed streams of data simultaneously. It smooths the power demand across the battery.
Oh, that makes sense.
Furthermore, modern power management chips inside the phone switch at hundreds of kilohertz or even megahertz to maximize efficiency.
So by raising the switching frequency of the internal chips, they push the incidental magnetic emissions way out of the extremely low frequency band that U-beta tested.
That's the entire mechanism.
Wow.
Our phones are basically metabolizing power much more smoothly now. The hardware evolved out of the biological danger zone inadvertently, driven purely by the engineering pursuit of battery life and data bandwidth.
Which brings us to a transition in the document that feels incredibly relevant today.
Yeah.
Because right now, in August 2026, the technology conversation is dominated by 6G, and there are massive rumors swirling around it.
Yes. We can call it the 6G phantom.
The 6G phantom, I like that.
The prevailing internet rumor is that 6G will extend into terahertz frequencies and expose the population to untested sub-terahertz radiation.
Yeah, I've seen those articles. They make it sound apocalyptic, like we're going to be microwaved.
You see headlines implying we are going to be bathed in military-grade microwave beams.
Yeah, right. What does the internal research actually say about the 6G rollout?
First, the author grounds us in the actual 3GPP timeline.
Which is what?
3GPP is the global organization that develops and freezes these cellular standards. The document notes that Release 21, which will deliver the very first normative 6G specifications, won't even be finalized until March 2029 at the earliest.
Oh, wow.
Commercial deployment isn't realistically projected until 2029 or 2030. So right off the bat, a lot of the current panic is just premature speculation about hardware that hasn't even been finalized yet.
The tech literally doesn't exist yet in a consumer form.
It doesn't, but more importantly, the document systematically debunks the terahertz claim.
Okay, good.
The frequency band that is actually under active adoption for the 6G radio access network, meaning the signal that will blanket cities and cover the public, is called FR3.
FR3.
This spans from 7.125 to 24.25 gigahertz.
Okay, so that is centimetric wave, upper mid-band. That is nowhere near terahertz territory.
It isn't. Sub-terahertz frequencies are certainly being researched, but only for backhaul extensions.
The backhaul meaning the connections between the cell towers themselves,
Yeah.
right? Not the connection to my phone.
Yes, exactly. Sub-terahertz frequencies have terrible mobility problems.
Like what?
They're easily blocked by leaves on trees, rain, or even just a person walking by. They simply cannot penetrate buildings or handle moving targets well enough to be used for consumer handsets.
So the realistic everyday public exposure question for 6G is squarely in that 7 to 24 gigahertz range.
Exactly.
But wait, haven't we been using that exact frequency range for decades?
We have. That band is heavily occupied by decades of aviation radar, weather satellites, and fixed point-to-point links. The frequencies aren't new at all. But the author points out a massive glaring blind spot in how we test the safety of these specific frequencies for consumer use.
Oh.
And here's the kicker. You cannot use chicken embryos to test 6G.
Why not? The eggs were the gold standard for testing the low-frequency magnetic pulses, right?
It all comes down to the physics of penetration. Above roughly 6 gigahertz, the penetration depth of radio frequencies into biological tissue collapses.
What do you mean collapses?
Remember, the calcium carbonate of the eggshell was essentially transparent to a 1 microtesla low-frequency magnetic field. The pulse passed right through.
Right.
But if you hit an egg with a 16 gigahertz RF signal, the high water content of the shell and the albumin entirely absorb the microwave energy right at the surface.
Ooh.
So the embryo inside wouldn't even be exposed to the primary radio wave. It would just sit inside a shell that is slowly warming up from the outside.
So the biological model of the embryo falls apart at these higher frequencies because the energy never reaches it in its original form.
Exactly that, which leads to the most concerning gap identified in the document, the wall-mounted antenna problem.
Yes. This is the part of the deep dive that really unsettled me. This is the hook we started the show with.
It's wild. It highlights a staggering disconnect between compliance engineering, the people who measure radiation to make sure a product is legally allowed to be sold, and bioeffects literature.
Right, the biologists who actually study what that radiation does to living tissue.
Yes.
Okay, set the scene for this blind spot.
So engineers are designing small, wall-mounted microantennas to get these higher frequency 6G signals indoors, because as we mentioned, they don't penetrate buildings well from outside towers.
Right.
The document cites a specific study, Elgasher et al., 2024, that modeled a wall-mounted microsite operating at these upper mid-band frequencies.
And what is the telecommunications industry's official position on the safety of these indoor microsites?
The industry position relies on spatial exclusion.
Spatial exclusion.
Yeah. They argue that the physical region where radiation exposure limits might be exceeded is incredibly small, only a few centimeters for small indoor antennas, maybe a few meters for rooftop ones.
Okay.
Their safety models assume these antennas are installed in locations where unauthorized people cannot access that immediate high radiation zone.
But the document points out a giant everyday flaw in that assumption, a shared exterior wall.
Exactly.
Like, if I live in a dense apartment building and the property manager allows a telecommunications company to bolt a 6G microantenna to the outside of my living room wall to boost neighborhood coverage, I am sitting literally inches away on the other side of that drywall.
Yep.
I have no notification, and legally, as a tenant, I usually have no procedural standing to stop the installation.
And here's where the dosimetry math, the calculation of how radiation is actually absorbed, gets genuinely concerning.
Okay.
Studies show that free space calculations are fundamentally flawed for indoor environments.
Free space meaning testing the antenna in an empty field or a sterile lab.
Yes. When you measure radiation in an empty room, the energy dissipates cleanly.
Right.
But when you move that antenna indoors or beam it through a wall into a furnished apartment, you introduce complex reflections. The signal bounces off metal appliances, mirrors, and concrete pillars.
Oh, wow.
This creates what engineers call multipath fading and standing waves. These reflections can actually cause constructive interference, making the average field levels and the localized absorption rates in the body higher in a realistic indoor environment than they would be standing the exact same distance away in free space.
That's terrifying. But surely the engineers know this. I mean, they have to model how the signal gets to my phone through the wall.
Oh, they do. The document notes that research groups like Theodore Rappaport's team at NYU have exhaustively mapped all of this penetration loss.
Okay.
They have precise data on exactly how 16 gigahertz waves pass through concrete, drywall, and low emissivity glass. The exact math of how much radiation gets through that wall is fully available.
But let me guess. The biologists studying the health effects don't use that math.
The biologists have never put a test subject in that exact behind-the-wall scenario.
Seriously.
Every single biological study looking at health impacts above 6 gigahertz puts the animal or the human subject in an anechoic chamber.
Which is what?
A room covered in foam cones that absorbs all reflections. They point the horn antenna directly at the subject in a straight, unobstructed line.
So every behind-the-wall study is purely an engineering compliance check to see if the signal connects, with absolutely zero biological endpoints measured.
Yes.
And every biological study uses an artificial, reflection-free, direct exposure setup that doesn't mimic living in a modern apartment.
That is the blind spot. The two departments are basically operating in parallel universes.
Unbelievable.
The engineers know how the wave changes passing through the wall, but don't measure the biology. The biologists measure the biology, but only using pristine waves that don't exist in a real apartment.
That is incredibly frustrating.
It really is.
But let's take a breath, because this is where the author of the document makes a massive lateral pivot.
Yes, the pivot.
Because you read all this dense analysis about 6G, drywall penetration, and chicken embryos, and you wonder, how does this possibly lead to the second document about building a tactile communication garment?
Right, a suit that vibrates to let you feel speech.
Yeah.
How are these connected?
The connection is brilliant. It comes down to one fundamental realization the author had while investigating cellular safety.
Which was?
To truly understand the biological exposure of a cell phone, you have to understand the shape of the signal. You have to understand exactly how the phone encodes human speech.
Okay.
What is the actual data stream traveling through the air? And decoding that data stream led to a revelation that became the literal foundation for the Tactile Suit project.
So let's cross that bridge. The section in the document mapping this out is titled, Why Your Phone Doesn't Speak English.
It is a counterintuitive title, but physically accurate.
Okay.
Most people assume that when you speak into a cell phone, the microphone records your voice, turns it into a digital audio file like an MP3, and streams that waveform over the cellular network to the other person. Yeah, that's what I assumed.
But that is not what cellular speech codecs do at all. They do not transmit language. They do not transmit phonemes, the building blocks of words.
If they aren't sending an audio waveform and they aren't sending the phonetic letters of the words I'm saying, what exactly is the phone transmitting?
They are transmitting a mathematical model of your physical vocal tract.
Okay, my brain just broke a little bit. Explain the mechanics of that to me.
Let's look at the GSM full-rate codec and the CELP family that replaced it, things like AMR and EVS, which your modern smartphone uses today.
Okay.
They rely on an algorithm called linear predictive coding, or LPC.
Linear predictive coding. How does it predict my voice?
Imagine building a digital robotic model of your throat, your tongue, your lips, and your vocal cords.
Okay.
Instead of recording the sound of your voice, the processor in your phone analyzes your audio in tiny 20-millisecond chunks.
Right.
For each chunk, it calculates the exact physical shape your theoretical vocal tract must be in to produce that specific sound.
So it is essentially reverse engineering the physical movement of my mouth in real time.
That is the entire mechanism.
Wow.
And the network doesn't send audio. It sends those predictive coefficients. It sends a data parameter for the pitch, which the engineers call the long-term predictor lag. It sends loudness updates every 5 milliseconds.
So it's just sending instructions.
Yes. The receiving phone on the other end of the call takes those mathematical instructions and uses its own internal synthesizer to rebuild your voice from scratch.
So when I am talking to my wife on the phone, I'm not actually hearing her voice.
No.
I am listening to a digital puppet of her, generated locally on my phone's hardware, based on invisible puppeteer strings being sent over the network.
That is a flawless analogy. It is acoustic resynthesis, not waveform transmission.
Wait, if it's just a mathematical model of a human vocal tract, what happens if I have a terrible cold and my throat is swollen?
Good question.
Or what if a parrot mimics human speech into a cell phone? Does the math break?
The math adapts. Yeah. If you have a cold, the acoustic resonance of your voice changes, so the algorithm calculates a different set of coefficients that represent a swollen vocal tract model.
Okay, that makes sense.
As for the parrot, the codec will try its best to force the parrot's squawk into a human vocal tract model.
That sounds hilarious.
It's often why background noises, like a siren or a dog barking, sound so weird and garbled on a phone call. The algorithm is desperately trying to synthesize a dog bark using a mathematical model of human lips and a tongue.
That is so deeply weird, but it makes perfect sense.
And we know definitively that the network isn't just transmitting linguistic phones, the actual letters of language, because the algorithm is good enough that you can recognize the specific identity and emotional tone of the speaker.
Right.
A codec that only understood linguistic phonemes would strip all the emotion out. You would just hear a robotic text-to-speech voice.
Which brings up the arithmetic proof the author uses in the document, which I found fascinating because it proves the bandwidth gap.
The math is undeniable. Human speech, on average, runs at a speed of about 12 to 15 phones per second.
Okay.
If you calculate the data weight of just the linguistic information, the raw text of the sounds being made, it is incredibly lightweight. It only takes roughly 70 to 80 bits per second of data to transmit the spoken words.
80 bits per second. But cellular networks spend a massive amount of data on a voice call. The document says anywhere from 4,750 to 13,000 bits per second.
Yes. So if the words only take 80 bits, what are the other 12,920 bits doing?
That massive gap is the acoustic detail.
Exactly. It is the data used to make you sound like you. It's the breathiness, the pitch, the regional accent, the emotional inflection.
Now, before we move on to how this connects to the tactile suit, I want to clarify something for you listening, because the author brings up a very common linguistic myth about phones.
Yes, this is important.
Sometimes you hear people claim that there are 130 universal phones that make up every human language on Earth. But the author completely dismantles this idea using the Kiev Soibel 2.0 database from 2019.
It is a crucial clarification. The Fioibel 2.0 database catalogs over 3,100 distinct segment types across more than 2,100 human languages.
Wow. Over 3,000.
Yes.
So a phone isn't just a universal acoustic bucket that you can drop sounds into. It is an internal contrastive category specific to a single language.
Exactly that. The document points out a great example. Hindi differentiates between a regular unaspirated P sound and a breathy aspirated P sound represented as P versus P grease.
Okay.
In Hindi, swapping those sounds changes the entire meaning of the word, but English doesn't care. To an English speaker's brain, both of those acoustic variations are lumped into the exact same P-phone bucket.
Language carves up the acoustic space differently depending on where you were born.
Yes, which is why the telecommunications engineers decided the phone network must ignore phonemes entirely. If they built a network that transmitted phones, it would only work for the languages it was programmed to understand. By modeling the raw acoustic output of the physical vocal tract instead, the network becomes universally language agnostic.
That is a stroke of engineering genius.
It is. But this realization about bandwidth is what dictates the entire design constraint for the second document.
The tactile sensory communication garment.
Yes.
How so?
Well, the ultimate goal of a tactile garment is to allow a user to feel human speech through vibrations or electrical impulses on their skin.
Right.
But human skin, especially on the torso, has incredibly low data bandwidth compared to human ears.
Okay.
You simply cannot pipe a 13,000 bit per second cellular audio stream into a shirt and expect the brain to understand it.
It would just feel like a chaotic, unintelligible buzz like grabbing a vibrating washing machine.
Yes, exactly. If we want to build a suit that actually works, we have to strip the speech down to that bare minimum 70 to 80 bit per second phonemic layer.
I see.
We have to throw away the 13,000 bits of acoustic detail, the emotion, the speaker identity, and just transmit the linguistic skeleton to the skin.
And that constraint introduces the project brief. The author lays out the goals for the garment and immediately tries to separate science fiction from physiological reality.
Which is so necessary.
Because tech companies have been promising this kind of feel-the-internet technology for a long time.
They have, and they usually fail because they overpromise.
Right.
The author defines 3 highly specific levels of ambition to keep the engineering grounded.
Okay, let's go through them.
Level 1 is a low bandwidth channel, just 5 to 10 bits per second of data. This would convey direction, range, and alerts.
Okay.
For example, a heavy vibration on your left shoulder means a car is approaching from the left.
Like the haptic feedback on a smartwatch or those navigation belts that buzz to tell you which way north is.
That's the mechanism. It is completely achievable and works well today.
Okay, what's next?
Level 2 is supplementary speech. This requires 8 to 14 bits per second. The suit wouldn't give you every single word in a sentence, but it would give you the prosody, the rhythm and timing of the speech-voice activity, and maybe the physical location of the talker.
Okay.
It is designed to supplement degraded hearing in a noisy room. It doesn't replace the ear.
And has level 2 been achieved?
By natural human-to-human methods, yes, but never successfully by a mass-market wearable device.
Interesting. And level 3?
Level 3 is standalone speech substitution. This requires 40 to 60 bits per second of pure linguistic content.
So this is the dream where a profoundly deaf person could listen to a complex conversation entirely through the vibrations on their shirt.
The holy grail of sensory substitution.
It is.
It is, and the document is brutally honest here. No device has ever approached this capability. It's currently impossible with modern hardware and should be treated as a deep, decades-long research question, not a near-term product target.
Because of the harsh biological constraints of human skin, we have to talk about the 6-centimeter rule.
Oh, yes. This is a binding physiological constraint established by researchers Novich and Eagleman in 2015.
Yeah.
They mapped the spatial acuity of the human torso. They found that if you want 2 simultaneous vibrations to be independently resolved by the brain as 2 distinct points, the stimulation sites must be at least 6 centimeters apart.
If you're listening to this, you can actually test this on yourself right now.
Yes, you should.
Take your hand and tap 2 fingers very close together on your forearm or your palm. Your brain easily feels 2 distinct taps.
Right.
But if you have a friend try that on the middle of your back, placing their fingers an inch apart, your brain just feels one big mushy tap. It completely blends them together.
That biological blind spot is the bane of tactile engineers. Because of that physical 6-centimeter spacing requirement, you can only fit about 60 to 80 distinct stimulation sites on the entire human torso.
So my back essentially has the resolution of a 1980s 8-bit TV screen.
That is a great way to put it.
How can we possibly send complex, high-speed conversational information through a screen with only 60 pixels?
Historically, many researchers believe we couldn't.
Right.
The author addresses a famous myth in the academic literature. The belief that human skin has a hard biological capacity limit of about 5 bits per second.
Which would mean Level 3's speech substitution, requiring 60 bits per second, is biologically impossible. The skin just couldn't carry the data.
But the author corrects the record. That 5 bits per second limit is not a biological ceiling of the skin itself.
Oh.
It is simply the limit of what a human subject can achieve when learning an arbitrary artificial vibration code in a laboratory over a short 12-hour training period.
Ah, so if you only practice reading Braille with your back for 12 hours, you hit a cognitive wall.
Exactly.
It's a learning limit, not a hardware limit of the nervous system.
Exactly that. When we look at natural methods cultivated over years, the bandwidth is massively higher. The document points to the Tadoma method as the ultimate proof of concept.
What is Tadoma?
It is a method of communication used by some individuals who are both deaf and blind. Helen Keller famously used a variation of it.
Oh, wow.
The user places their hands directly on a speaker's face and neck. Their thumb rests on the lips. Their fingers fan out over the jaw and the throat to feel the vibrations of the vocal cords and the expulsion of air.
Feeling the physical mechanics of speech.
Yes, and experienced Tadoma users can receive connected conversational speech at 60 to 80 words per minute.
That is incredibly fast.
It is. If you calculate the data rate of that comprehension, it translates to 12 to 14 bits per second.
Wow.
It takes years of total immersion to learn, but it physically proves the tactile channel is substantially wider than those 12-hour lab tests imply.
Okay, but I have to play devil's advocate here.
Sure.
Tadoma uses the hands. The fingertips are packed with nerve endings. They are incredibly sensitive. We are talking about building a suit worn on the torso. My back does not have the sensitivity of my fingertips.
And that brings us to one of the most crucial physiological revelations in the document. The profound difference between hairy skin and glabrous skin.
Glabrous skin being the smooth, hairless skin on our palms and the soles of our feet.
Yes. The document cites a pivotal study by Mons et al. From 2006.
Right.
They compared the sensory capabilities of the fingertips against the dorsal forearm, which represents the hairy skin covering the rest of our bodies.
Right.
As expected, hairy skin has terrible spatial acuity, the 8-bit TV screen you mentioned, and its detection threshold is much higher. You need a physically stronger vibration to even notice it's there.
Because hairy skin and glabrous skin literally have different types of mechanoreceptors underneath them, right?
Yes. Glabrous skin is dense with Meissner's corpuscles for fine touch. Hairy skin relies more on nerve endings wrapped around the hair follicles themselves.
Oh, interesting.
So the torso is objectively worth figuring out where a vibration is, and it needs a louder shout to hear it at all.
So the suit is doomed.
No, because of a massive breakthrough finding in that same study.
What was it?
While the spatial resolution is terrible on the torso, the frequency discrimination is strikingly similar between the hand and the back.
What, it really? So my back can't tell exactly where a vibration is, but it can easily tell the difference between a low hum and a high pitch.
That is the mechanism. The ability of the nervous system to distinguish between different frequencies survives the move from the sensitive fingertips to the dull torso.
That's amazing.
The design consequence for the garment is immediate and absolute. If you want to encode complex data on the torso, do not rely on spatial maps. Do not try to draw letters on the back. Rely on pitch and frequency.
That is brilliant engineering. It is working in harmony with the biology instead of fighting it.
Exactly.
Which brings us to the history lesson of the document. Because tech companies have been trying to build tactile suits for 70 years, and they essentially all failed to become widespread tools. Section 6 is basically an autopsy of those failures.
And it is a ruthless autopsy. The author reviews a graveyard of devices: Vibratys in 1957, tactile vocoders in the 1970s, the Opticon, the TVSS camera on the back system, all the way up to modern phonemic sleeves.
Why did they all ultimately fail to catch on?
The primary failure point, echoed across decades of literature, is the insurmountable gap between cognitive and perceptual integration.
Cognitive versus perceptual. Explain the difference in how the brain processes those.
Think about the act of reading a book. When you were a 5-year-old child, reading was a heavy cognitive process.
Right, sounding out the letters.
Exactly. You had to look at the letter C, consciously sound out coo, look at A, sound out ah, and blend them. It took massive conscious effort and memory.
But as an adult,
reading is perceptual. You look at a word, and the meaning simply arrives in your brain automatically, effortlessly. You cannot stop yourself from reading a billboard if your eyes pass over it.
the brain handles it in the background. I don't have to dedicate RAM to it.
Exactly that. The fatal flaw with almost all historical tactile suits is that the users never achieved perceptual integration.
They never got to that automatic stage.
Right. They learned the complex vibration codes, sure, but they always had to actively, cognitively translate them.
Oh, that sounds exhausting.
It is. They had to think, okay, a buzz on my left shoulder followed by a high pitch means the letter T. They had to constantly dedicate conscious attention to deciphering the suit.
Which means if you were trying to walk down a busy street, avoid traffic, or hold a conversation, your brain just gets overloaded. The cognitive load is too high to sustain.
It is exhausting. To prove how stubborn the brain is about this, the author cites an incredible experiment by Rizza and colleagues.
What did they do?
They had human subjects trained for 50,000 trials.
50,000. That is days of intensive, grueling training.
It is. They were trying to force the brain to associate specific tactile vibration patterns with specific spoken syllables.
Okay, why?
The ultimate goal was to see if they could induce a tactile McGurk effect.
I know the McGurk effect from psychology class. That's the sensory illusion where what you see changes what you hear.
Exactly.
Like if I'm watching a video and I hear an audio track of someone saying bah, but their lips are clearly mouthing the word fa, my brain actually hears the sound tha.
Yes. Visual input perceptually overrides the auditory input because the brain merges those two senses automatically in the background.
So Rizzo wanted to know if his suit could do that.
Right. Rizzo wanted to know. After 50,000 trials of grueling training, would a tactile vibration seamlessly change what the subject heard? Would the skin integrate with the ear?
And what was the result?
Zero perceptual integration. None at all.
None.
The subjects correctly reported the auditory sounds completely independently of the tactile stimulation.
Wow.
They were highly accurate at cognitively translating the buzzes when asked, but the brain kept the two streams of data strictly segregated. The suit never became a true sense.
So we have a 70-year history of engineers forcing the brain to do math instead of just letting it feel the answer. How do we fix it? How do we trick the brain into accepting a vibration as a seamless sense?
The author brings up a framework called the Jane criteria.
Okay, what is that?
Jane, Fuller, and Backus created a psychological framework detailing exactly what factors favor perceptual integration of a new arbitrary cue.
Why the brain sometimes merges senses effortlessly, like sight and sound, and sometimes refuses to.
Exactly.
What are the criteria to trick the brain?
The cue should ideally be intrinsic to the stimulus. It should ideally be from the same sensory modality, and crucially, it should not contain too much information.
Wait, lower information is better for the brain. That seems counterintuitive. I would think more data is better.
For conscious analysis, more data is better. For automatic perceptual integration, high data is a blockade.
Oh, I see.
An arbitrary tactile code that tries to spell out every single foam in the English language utterly fails the Jane criteria. It is too complex, it crosses sensory modalities, and it is overwhelmingly high information.
So the brain rejects it as an automatic sense and forces you to use your conscious cognitive processor.
Yes, but a low information cue like a single simple vibration indicating voice activity or a basic pulse showing which side of the room the speaker is standing on, that simple signal satisfies the criteria.
So the lesson for the engineers is to start stupid.
Basically, yeah.
Start with a very low resolution, simple signal, and let the brain absorb it naturally.
That is the foundation. And there is one more critical historical lesson that the engineers missed for decades. The active versus passive problem.
Oh, this is where Bacurita comes in. The TVSS system.
Yes. In 1969, a neuroscientist named Paul Bacurita built a remarkable system called the Tactile Vision Substitution System.
What did it do?
He took a heavy video camera and translated the black and white pixels into a 20 by 20 grid of vibrating pins pressing against a blind person's back.
He literally strapped a low-res TV screen made of vibrating needles to their skin.
And here is the astonishing finding that the engineering field routinely overlooks when building these devices.
Tell me.
If the blind subject was passive, meaning they just sat motionless in a chair while the researchers pointed the camera at objects like a cup or a phone, their ability to recognize the object was never better than random chance, even after dozens of trials.
So the brain just felt random, annoying, meaningless tickles on the skin.
Exactly, but what if they were active?
Active meaning they moved.
If the subject took physical control of the camera themselves, panning it around the room with their own hands, tilting it, zooming it in and out, they rapidly developed substantial form recognition ability. They started seeing the objects.
Because their motor system was driving the input.
Yes.
Let me use an analogy. If I am sitting perfectly still and someone traces a complex map on my back with their finger, it just feels like a confusing massage. I can't picture the map.
Right.
But if I physically lean my body to the left and the vibration on my back instantly moves to the right in response, my brain intuitively says, ah, that is a spatial environment. I'm navigating around an object. You have to be the one driving the car to learn the route.
The physical movement provides the necessary context that allows the brain to map the sensation automatically. It converts slow, effortful cognitive learning into fast, automatic perceptual mapping.
So if we synthesize all of this, the 6-centimeter spatial limit of the back, the survival of frequency discrimination, the need for low information cues to achieve automaticity, and the absolute necessity of active movement, the author essentially has a literal step-by-step roadmap for how to engineer a tactile suit that actually works.
And that is exactly what Section 7 delivers, engineering the fix.
Let's get into it.
The document lays out the highly specific hardware and software solutions proposed for this new garment.
Let's start with the encoding software. how do we actually translate the data into vibrations on the skin, knowing everything we know now?
The author relies again on the work of Novich and Eagleman, who proved that the best primitives, the most effective basic units of sensation for the torso, are spatiotemporal sweeps.
Spatiotemporal sweeps.
Mhm.
So not just a static buzz on one spot, but a feeling that moves across the skin over a set period of time.
Yes, moving patterns taking about 60 to 100 milliseconds to complete their path across the torso.
Okay, why moving patterns?
The motion of the sweep overcomes the poor spatial resolution limits of the hairy skin. Ah, clever.
And the author highlights an even more powerful, massively underused dimension for encoding information: rhythm.
Rhythm, like literal musical rhythm, tapping out a beat.
The document points out that music is the ultimate biological proof that human beings can automatically, effortlessly parse incredibly complex temporal structures.
That's so true.
You don't have to cognitively think about the beat of a song to tap your foot to it. Your nervous system just absorbs the rhythm and syncs to it.
It's just automatic.
If one dimension should be heavily invested in for this suit, it is rhythm, because rhythm completely bypasses that cognitive bottleneck.
That makes total sense. But what about processing speed?
Right.
If I am standing in front of you listening to you talk, and the suit is buzzing along to your voice, how fast does the software have to be?
This is a hard, absolute, non-negotiable specification in the design: latency.
Latency, okay. To achieve perceptual binding, which is the moment your brain fuses the vibration on your chest with the sound of the voice hitting your ear into one unified experience, the tactile signal must hit the skin less than 50 milliseconds after the audio hits your ear.
50 milliseconds.
Mhm.
That is a fraction of a blink of an eye.
It is incredibly fast. If the software processing lags by 200 or 300 milliseconds, the brain registers the sound and the vibration as two completely separate, unrelated events.
It breaks the sensory illusion.
It breaks the illusion and you fall right back into cognitive translation.
But hold on. Earlier we discussed how the speech has to be mathematically stripped down to phonemes to fit the low bandwidth of the skin.
Yes.
Running complex speech recognition software, calculating phonemes, figuring out the math that inherently takes hundreds of milliseconds of processing time. You can't do that in under 50 milliseconds.
And that is the central tension of the entire design.
Oh.
Phonemic coding is mathematically correct for solving the bandwidth problem, but it is physically too slow to achieve perceptual binding.
So how does he fix it?
The author solves this paradox by proposing a two-layer software architecture.
Two layers running at the same time.
Yes. The first layer is ultra-fast, hitting the skin in sub-50 milliseconds, but it carries very low information.
Okay, what does it carry?
It doesn't analyze words, it just derives basic acoustic signals directly from the raw audio, like the fundamental frequency of the room or raw voice activity. Is someone speaking and how loud are they?
Just the basics.
Yes. This fast primitive layer acts as the sensory glue. Its only job is to perceptually bind the suit to the real-time audio environment.
It tricks the brain into accepting the suit as an extension of the ear.
Exactly that. And once that foundation of trust is laid by the fast layer, the second layer, the slower symbolic phoneme layer carrying the actual linguistic content, which might arrive 200 milliseconds late, can ride on top of it.
Oh, wow.
The brain accepts the late data because the fast layer already established the connection.
That is software wizardry.
It really is.
Okay, that handles the code. But what about the physical hardware? We have to actually stimulate the skin. The document outlines a massive engineering debate here between two distinct technologies: vibrotactile and electrotactile.
This is where the physical engineering gets incredibly difficult.
Okay, break them down.
Vibrotactile technology uses tiny mechanical motors to physically vibrate the skin, very similar to the pager motor inside a cell phone.
Right.
Electrotactile technology skips the mechanical motor entirely. Instead, it passes a tiny, highly controlled electrical current directly into the skin to stimulate the nerve endings beneath the surface.
And the document notes the author originally wanted to use electricity, right?
He did. His originating interest came from prior therapeutic uses of electrical stimulation on injured muscles.
Okay.
From an engineering standpoint, electrotactile is a dream. It makes the suit lighter, it draws vastly less battery power, and it has zero moving parts to break.
Sounds perfect.
But the document offers a brutally honest assessment. Electrotactile is an absolute nightmare to implement in the real world.
Why is passing a tiny current into the skin so hard?
One word: impedance. Electrical resistance.
Ah, okay.
Human skin is a wildly unpredictable material when it comes to conducting electricity. Its resistance changes drastically based on how much you are sweating, how hydrated you are that day, the density of hair follicles in a specific square inch, and even how tightly the garment is pressing against a fold of skin when you sit down.
So a shock that feels like a gentle, informative tap on my dry back while I'm sitting on the couch might feel like a hornet sting if I walk outside into the heat and start sweating, because the sweat lowers the resistance.
That is the exact hazard. The usable sensory window between "I can't feel this at all" and "this actively hurts me" is incredibly narrow.
Ah,
And it shifts millisecond by millisecond based on your sweat. If you have a shirt with 60 electrical nodes on it, every single one of those nodes is facing a completely different, constantly changing impedance environment.
let me use an analogy here. It sounds like trying to drive a car where the physical weight of the vehicle randomly changes from a lightweight bicycle to a massive semi-truck every 3 seconds, depending on the weather.
That is a great visual.
You would have to constantly slam on the brakes just to test how hard you need to push the pedal.
That captures the chaos perfectly, and
Right.
that testing the brakes concept is precisely how they propose fixing the impedance problem.
Really?
Yes. The necessary engineering innovation is called closed-loop current control, and it has to happen independently at every single electrode.
How does closed-loop control work?
The system has to constantly send a tiny subsensory test current into the skin to measure the local electrical resistance at that exact microsecond.
Okay.
The processor calculates the required voltage to safely overcome that specific resistance and then delivers the actual informational pulse.
And it does this constantly.
It has to do this loop hundreds of times a second for every electrode independently.
It has to adapt to the sweat on your back millisecond by millisecond.
Yes, and the author specifically calls out a misguided proposal that someone in the field apparently made. The idea of placing a few microneedle sweat sensors around the body to generally measure how much the person is sweating, and then guessing the impedance for the whole suit.
That sounds logical to me. Why is that a bad idea?
Because human sweating is highly localized and asymmetrical.
Oh,
A sweat sensor located 6 centimeters away on your shoulder tells the computer absolutely nothing about the exact patch of skin trapped under a specific electrode on your lower back.
that makes sense.
The solution isn't sparse sensors. The solution is that every single stimulating electrode must simultaneously act as a sensing electrode.
The document mentions using hydrogel electrodes first, but then it holds microneedles in reserve as a future option. What is the deal with microneedles?
Microneedles are fascinating. They are microscopic structures designed to penetrate the very outermost layer of dead skin, the stratum corneum.
So they literally break the skin barrier.
They do, but they are so short that they don't reach the deeper pain receptors or the blood vessel.
Okay.
By bypassing that dead layer of skin, which is the primary source of electrical resistance, microneedles drastically lower the impedance and artificially widen that usable window between sensation and pain.
They solve the physics problem beautifully by just tunneling under the barrier.
They do, but the author argues strongly against using them for the initial prototypes due to practical reality.
Why?
If you are wearing this suit every single day, sweating in it, taking it off and throwing it on a chair, microneedles present a massive, unacceptable risk of physical breakage, skin irritation, and severe regulatory headaches regarding medical devices and infection.
Yeah, nobody wants a bunch of broken needles stuck in their back.
Exactly. The firm recommendation is to force the engineers to make the software and the hydrogels work first.
Okay, so let's imagine they succeed. They build this perfect suit. The closed-loop hydrogels handle the sweat. Two-layer software achieves 50 millisecond latency. We have a working device,
Right.
but we still face the biggest hurdle of all, training the human brain to actually use it.
And this psychological hurdle is where almost every well-funded tactile project in history met its end.
Okay, lay it out for us.
Training a human nervous system to acquire an entirely new sense is incredibly delicate. The document leans heavily into a psychological phenomenon called Kamen blocking.
Kamen blocking. Let's unpack the mechanics of that.
The best way to understand Kamen blocking is to look at neuroplasticity. We know the phrase, neurons that fire together wire together, that is Hebbian learning.
Right.
But what Kamen blocking proves is that the brain is ruthlessly efficient. It will actively refuse to wire new neurons if an easier pathway already provides the answer.
Give me a real-world example of that.
Imagine you were trying to learn how to navigate a complex city using just a physical paper map in the position of the sun.
Okay.
But while you are practicing, you have a GPS on your dashboard loudly screaming turn-by-turn directions at you.
I would just listen to the GPS and totally ignore the map. It's the path of least resistance.
Precisely. In the failed tactile suit experiments of the past, researchers strapped the vibrating suit onto the subjects, but they also let the subjects listen to the full, clear audio of the words at the exact same time.
Oh.
The auditory channel, the earfully, predicted the answer with perfect fidelity. Therefore, the tactile cue on the skin was entirely redundant.
So the brain just categorized the vibrations on the suit as useless background noise and gated it out. The skin neurons never wired together with the language centers.
Yes. Because the auditory channel was intact and vastly easier to use, learning the tactile channel was neurologically blocked. The brain literally refused to expend the metabolic energy to rewire itself for a redundant signal.
So how do we force the brain to care about the suit? How do we break the Kamen block?
The author's solution is a progressive degradation protocol.
What does that mean?
You don't just put the suit on someone with perfect hearing and wait for magic to happen. From day one of training, you have to artificially degrade the audio the person is hearing. You narrow the frequency bandpass, you add white noise to their headphones.
You intentionally make their primary sense unreliable.
You have to. The document draws a brilliant physiological analogy to unilateral hearing loss.
Okay.
When a person loses hearing in one ear, they instantly lose the ability to locate where sounds are coming from using binaural differences, comparing the timing between two ears.
Right.
Suddenly, to survive, their brain has to rely on monaural spectral cues, meaning how the physical shape of the remaining outer ear changes the sound and dynamic cues from physically turning their head.
Cues they always had access to, but ignored because having two working ears was just easier.
Exactly. Biological necessity drives the reweighting of the senses. To train the brain to use a tactile suit, the engineers have to artificially manufacture necessity. The protocol demands interleaving brief, entirely unpredictable audio dropouts several times an hour during training.
So you're walking around with your suit on, having a conversation, and suddenly the audio in your earpiece just cuts out to static for 2 seconds.
Yes. And for those 2 terrifying seconds, the tactile channel vibrating on your back becomes load-bearing.
Wow.
It is the only physical way your brain can get the conversational information. That unpredictable necessity forces the nervous system to stay alert to the tactile stream and integrate it. The brain realizes, I might lose my hearing at any second. I need to keep this skin channel open.
That is beautifully devious engineering of the human mind.
It really is.
And it leads to a really important reframing of the entire project's ultimate goal. The author concludes that we need to completely abandon the idea of standalone speech substitution.
Yes. The historical endpoint for all these failed companies was always to replace hearing entirely. But framing a tactile suit as a replacement sets it up to fail against an impossible biological standard.
Because of the Tadama speed limits we talked about.
Right. Remember Tadoma. It takes years of intense immersion just to reach half the speed of normal hearing.
So if we aren't replacing the ear, what is the new achievable goal for this technology?
The goal is supplementation, building a device that functions in a crowded, noisy room to help you separate overlapping voices.
A device that bridges the gap when the ear temporarily fails or is overwhelmed. A device that supplies spatial information, like the azimuth of a moving target, that the human ear naturally struggles with in highly reverberant spaces.
You frame it not as a replacement ear, but as an entirely new, parallel sensory organ that excels exactly where the ear is weak.
That is the vision. And the final recommendation of the document is a strict build order.
Which is?
Step 1 for the engineering team isn't tackling speech at all. Step 1 is building a spatial demonstrator. Azimuth, range, directional cues.
Because it is low bandwidth, non-arbitrary, and highly active, it checks all the Jane criteria immediately, allowing the brain to integrate it quickly.
Exactly. It de-risks the physical hardware, it proves the hydrogels work, and the suit is wearable before they tackle the monumental, decade-long task of encoding linguistic phones.
Wow. What a journey.
Yeah, it's a lot to take in.
I mean, from unpacking a 1994 study about fast magnetic pulses killing chicken embryos to debunking the 217 hertz cell phone radiation myth, exposing the literal blind spot in how telecommunications engineers test 6G antennas through apartment drywall,
Right.
realizing that cellular voice codecs don't send audio waveforms, but rather mathematically resynthesize a digital puppet of our vocal tracks.
Yeah.
And finally, using that exact mathematical bandwidth limit to design a tactile suit that bypasses our cognitive bottlenecks and plugs directly into our perceptual nervous system.
It is a masterclass in interdisciplinary synthesis.
It really is.
It proves how asking a rigorous skeptical question in one isolated field like RF bioeffects can hand you the exact missing physical puzzle piece for a 70-year-old engineering problem in another.
It really does. And it leaves me, and hopefully you listening, with a profound concept to mull over.
Let's hear it.
If engineers can eventually master this closed-loop impedance problem, if they can map digital technology directly into our automatic perceptual system, using a low-information tactile cue that completely bypasses cognitive translation, where you don't even have to think to feel the data stream, where exactly does the human nervous system end and the digital device begin?
It becomes a completely blurred line. The suit becomes an artificial organ.
Exactly. If your skin can seamlessly process the acoustic rhythm of a crowded room or the exact location of a moving vehicle behind you without you having to actively dedicate conscious attention to it, your biological body effectively becomes a direct antenna for the digital world.
Wow.
What other invisible data streams, Wi-Fi traffic, atmospheric pressure, the emotional state of a crowd could we physically feel if we just found the right frequency to bypass the brain's cognitive firewall?
Once the diagnostic muddy waters of the biology clear, the possibilities for sensory expansion are just boundless.
Something to think about the next time your phone buzzes in your pocket. Thank you for joining us on this deep dive into the hidden mechanics of the digital world. Stay insanely curious.